Hello, ATS 570 students. This is Dr. John Schrage, and I am here today to talk to you a little bit about the use and application of filtering in atmospheric sciences. Filtering is a way of processing data. It is a technique that you typically use on a time series of data, where you have observations of some quantity over a period of time, and you want to make the data filtering. You want to represent the long-term processes in ways that you can remove the short-term processes. I'll show you a good example of it. Here's an example of a graph of something we call in the Southern Oscillation Index. If you're a survivor of tropical meteorology or some of the other classes here in our department, you know that the Southern Oscillation Index, or SOI, is a measure related to the phase of El Nino and La Nina. And it's something that we have been observing for a very long time, more than 100 years in the atmospheric sciences. And it's a relative, even though we only have monthly values of it, it is a fairly noisy quantity. Noisy in the sense of that it jumps up and down a lot. It has a lot of noise in the data just due to smaller scale weather disturbances other than El Nino. Probably the best way for me to illustrate what I'm talking about when I say that the data of the Southern Oscillation Index is noisy would be to just sort of jump ahead. If you have the PowerPoint in front of you, I'm jumping to slide 76 just to show you what I'm talking about here. But if we just zoom into like a few year period of this is a 10-year period of the data that we showed earlier, the curve that has all the little wiggles there, that's our Southern Oscillation Index. And you see that it has just a lot of little wiggles and so on. Well, that's not El Nino. El Nino are those big dips in the Southern Oscillation Index, like what you see there around 1992, 93, or again around 97, 98. Those are the El Nino events. That's what's most important to us. And so it would be neat to have a technique where we could remove all those little wiggles from the data and just only be able to have left the signal that's important to us. Well, there's a lot of different techniques by which that can be done, and some of these techniques are better than others, and they have different properties. The different properties are what we're actually going to focus on in the second presentation associated with filters. For now, I want to show you some of these different techniques. One of them, of course, is this business of taking the running mean, taking the average over a period of time. If you are talking about like the value at January of 2000, maybe you want to take the average of the 12 months on either side of it. So you want to have like a 25-month running mean centered on January of 2000. So you have like the 12 months before, also January 2000, and the 12 months after. That window of time is called a window, or actually in statistics they call that a boxcar for a running mean. And we actually denote it as having a width of 2k plus 1. In other words, like if we were talking about that window before, k would be 12, where the average at time I is the sum of all the values from time I minus 12, or I minus k, to the value at I plus k, or I plus 12. And so at every value of I, where I is just the increment along the time axis, we are just adding up the values from I plus k and from I minus k to I plus k, and then we just divide by 2k plus 1, and this is an average. And you can compute this running mean at every time I, and it works throughout the whole data series, except when you get near the beginning and near the end of the time series. If you're closer than k values to the beginning or the end of the data set, then the running mean becomes undefined. There aren't I minus k there isn't an I minus kth observation because you're off that's before the start of the data. And so you lose k values at the beginning and at the end of your time series. On the other hand, if your time series is fairly long and or your value of k is fairly small, your window is not particularly wide, this can be a perfectly acceptable trade-off. And so, like, for example, in this little example that we're going to be doing here using Excel, we're going to compute a 9-month running mean. And we're going to use Excel to compute a running mean of some data here. So I have some data here. These happen to be the Southern Oscillation Index, and you'll have this spreadsheet to work with and see. We're going to compute a 9-month running mean of the Southern Oscillation Index. And since we are talking about a 9-month running mean, the window is 9 months wide. It's always going to be an odd number. Then k is apparently equal to 4, because that way 2k plus 1 is 9, and we're going to work from the I minus 4 to the I plus 4 observation at each time I. So if we wanted to do this, we're going to first take in Excel, we're going to move our cursor down to the k plus 1th observation. Remember, there's no way to compute the running mean earlier than that because there aren't observations earlier than our first observation. Now, so here I am, I've moved down to the 5th observation, that would be, since k is 4, k plus 1 is 5, and I'm going to enter a function. Now in Excel we have this nifty function equals average, and so we're going to take advantage of that. I'm going to say equals average, and then I'm going to drag the cursor across the 2k plus 1 observations that I want to include in my average. So see how my, kind of graphically there, my value that I am trying to compute, where I have that formula, is equal to, you see how it's the middle of that range there that is 9 months wide. So it is a average of those 2k plus 1 values. Now in Excel I just hit return after I've highlighted those values, and I have now computed the 9-month running mean of the Southern Oscillation Index at just one point in time. Now the running mean itself is a time series, and so we take the average of, we take that value there, and we're going to copy and paste it down through the rest of this, the data here to compute the running mean at every observation time. The good news is this is a relatively simple thing to do in Excel because this is a relative reference problem. We don't need to use that business of dollar signs or anything like that. It's a pretty straightforward thing. We're just going to copy the selected running mean that we've already computed, and then we're going to select the range where you want that value copied to. We're going to copy all the way down through all that data except the last k observations because the running mean is not defined beyond that. We would be missing data. So you can take a look at this and see, you can actually, look at the actual formulas at each of your cells and make sure that you did this correctly. Like in this case here, I have the cursor parked on the last running mean that I computed, and I can look at the formula and see that the running mean that I computed refers to the correct group of 9 cells. Okay, so this running mean itself is a time series. We could plot it along with the unfiltered or unsmoothed data on the same graph like I have here. It's a little hard to see when you're looking at the full scale of 100 and some odd years of data to see how this exactly helped. But if I just zoom back in on those 10 years that we were looking at before, you can see how the original data, which has all the wiggles and so on in there, is plotted, but so is this new smoothed curve that is based on the running means. And it looks a lot better. I mean, the improvement in the data, a lot of those little wiggles are gone, and the long-term features like El Nino and La Nina are still there. The periods where the Southern Oscillation Index takes big swings, negative or positive, are still quite clear, but all the little wiggles have been removed. Running means are done all the time in atmospheric sciences and in science in general. They are a very useful way of computing this kind of smoothing data. They are very intuitive, they're relatively easy to compute, but as you'll see in the homework, they have some unfortunate properties. This is in many ways the worst possible way to smooth the data, but it's intuitive and people know about it, and so it tends to be the way we do it. But it is not the best tool for the job. Rather, what we really need is what we call a filter. Now, what I did is I went to the Glossary of Meteorology's website and just put in Bandpass Filter. And we'll learn about this word bandpass in just a little bit, but I just thought I'd give you a dictionary definition of a bandpass filter. A bandpass filter, according to the Glossary of Meteorology, is a digital, electrical, or mechanical system designed to attenuate signals outside of a frequency band while passing the signals within the band relatively unchanged. In our case, a bandpass filter is an algorithm. It's a set of equations that we're going to be using to do something to original data so that it has the properties we want. It keeps things we want to keep, but gets rid of other things in terms of noise. This word bandpass is easy to get hung up on. Actually, bandpass is just one of 3 types of filters. There's low pass, high pass, and bandpass. And just to be real clear here, all of the filters are going to be described in terms of their frequency. The frequency in sense of like every little oscillation that's in there, what is the frequency of that oscillation, where frequency is like 1 over the period or the distance between the time between one peak and the next. So you have to watch your units here. Like if you're working with monthly data, your units of frequency are per month. If you're working with daily data, then your units of frequency are 1 over day. A low pass filter is going to pass through or keep the low frequency things. That's most of the time what you're looking for in a filter is you want to keep the low frequency things, the long-term oscillations, like Southern Oscillation and El Nino or something like that, and remove the high frequency stuff that's just noise. In contrast, sometimes you need to get rid of the low frequency stuff and keep, those little wiggles, they're not the noise, that's what you're trying to study. In which case you want to remove the long-term trends and things like El Nino and so on and keep just the higher frequency stuff. That's a high pass filter. It keeps the high frequency stuff and gets rid of the low frequency stuff. And then finally there's the more complicated situation of the bandpass filters where you are trying to get rid of the frequencies that the noises in the data that are higher frequency than some cutoff, and also the ones that are lower than some cutoff, and you're just keeping things that have time scales over some specific range or frequencies over some specific range. If you were trying to study the diurnal cycle in data, you might want to remove the long-term signals like seasons or something like that, but you might also want to remove high frequency signals that might have to do with like noise or instrumentation errors or something like that. So we have high pass and low pass and band pass filters, but they all work quite similarly once you understand how filters in general work. To understand how filters in general work, let's think back to our idea of a running mean and rethink it and what those equations really meant, because actually filters are going to work remarkably similarly. Earlier, when we had the definition of running means, we used an equation that looked like this. Basically, at every time I, the running mean of x at x bar of I, was just the sum over the range from j is less than k, j is equal to negative k to j is equal to k of x of I plus j. In other words, we're adding up from I minus k to I plus k, and then we're dividing by this constant 2k plus 1, the number of observations that were in our boxcar or our window here. But that could just as easily be rearranged like as I'm showing here. I mean, it's not tremendously exciting to do so. It's just a little bit of algebra here to pull those weights out as their own fraction there. And then, in fact, we could call that number 1 over 2k plus 1. We could give that a name. We're going to call that a weight. And I'm going to give that number a weight W, and I'm going to call that WJ, where actually I have weights at every value of J from J equals negative K to J equals K. Now, in this case, all the weights are the same number. They're all equal to 1 over k plus 1, which is not such an exciting possibility. That's why we don't normally think of filters this way. But in fact, of running means this way. But in fact, it's correct. Effectively, we're taking each of the 9 observations in this case that we're using in that running mean, and we're taking that observation times some weight, and then adding the next observation times some weight, and then the next observation times some weight. In the case of an average, they're all the same weight, and it makes more sense to add up all your observations than to one time do the division, but it could work. You could imagine that this would be another way to do it. The right mathematical term here is we're going to say that we're going to convolve the data with these weights. Now, there's actually going to be another presentation and video. I'll have sent you the link and so on about what a convolution is, just in case that's a new term for you. It often is for students. And we are going to be convolving the data with these weights. Now, in the case of the running mean, it was not such an exciting thing. We're going to make a set of these weights in Excel, and we're going to convolve them with the data. Excel doesn't use the word convolve. They use this made-up word of sum product. But sum product is a good explanation of what a convolution is. You take the sum of the products. You multiply the data times a weight, and then you add that to the next data point times a weight. And then, so it's a sum of products. I don't know why they don't just use the right mathematical term and call it a convolution. So we could have computed the running mean in Excel using a convolution or a sum product. And so just to show that it could be done, let's go ahead and do it. First we need to compute the weights. The weights are going to be from values of W at WJ where J equals negative 1, J equals negative K, all the way up to WJ where J equals K. So we're going to have, in this case, since K was equal to 4, remember we had a window size of 9, so our value of K is 4, so that 2K plus 1 equals 9. So we're going to have 9 weights. And now in this particular case, they're not so exciting. The 9 weights are exactly the same. I'm going to make myself a little table over here of weights where each one is equal to 1 over 2k plus 1. And if I did this correctly, we can add up the weights, and the weights are going to add up to 1. That's a way to check your work. All right, now to actually convolve the raw data with this value, with these weights over here, we're going to use that equals sum product function. And so how we're going to do that here is we're going to put the cursor onto that first location, that first time when it is actually possible to compute a running mean, and we're going to enter the equals sum product function. Equals sum product and then open parentheses. Then what we're going to do here is we're going to use the mouse and we're going to drag across those first 2k plus 1 observations, those first 9 observations of data. Now, we also need to tell the equals sum product function what the weights are, and we're going to do that by pressing comma, and then we're going to drag across the weights. So the equals sum product function has 2 arguments, a range of data and a range of weights. Once you've chosen both the data and the weights, you press enter, and you'll notice that your running mean was computed using these weights and also comparing it to the value used next in the cell right next to it where it was done using the equals average function, and you'll find out that they are, of course, exactly the same if everything was done correctly. Well, now we need to apply that same equals sum product function to the whole time series, but now there's a problem. This is not going to be a relative reference problem. I mean, if I just tried to select that calculation we did and copied it down, something clearly quickly goes wrong. And if you examine the cells, the problem is as we copy that function down, the weights were still a relative reference. And so we were moving down in that list of weights, getting more and more missing values from below our little table of weights there. The lower cells are not pointing to the correct weights. We need to make those references to those weights an absolute reference. So what we're going to do is we're going to put dollar signs in before the row and the column of both the first and the last cell in that range of weights. Go back to your first cell in the running mean time series and press F2. F2 is the edit key in Excel. And you're going to go in there and you're going to edit this function so that your sum product is, you still have a relative range of data, but you have an absolute range of weights. They're always in the same rows and columns. And if you press enter, you'll notice that for that cell the value hasn't changed. And if you copy that cell through your whole list of data, you will take a look and you'll notice that the values now always match what we computed using equals average. And if you look at the actual equations, you'll see that we're convolving the last 9 observations, in this case, back there with the original weights back up near the top of the spreadsheet. That's good. That's the way it was supposed to work. Running means involve a very simple set of weights. This business of all the weights were just equal to 1 over 2k plus 1 was a simple way to do the convolution here. But it also produced a fairly poor example of smooth data. Filters do the same thing, but they do it better. But they have more complicated equations for determining the values of the weights. So running means are not necessarily such a great way to do this business of smoothing. There are all these filters that other people have developed in which there are different weights that you create, which you convolve with the data that have different properties and make a better smooth version of the data. And the first example of such a filter I want to show that we're going to be working with this class is called the Lanczos filter. Lanczos is just one of a whole set of different scientists over the years who have developed different filtering techniques. And we're going to work in particular with the low-pass version of the Lanczos filter because Lanczos filter well, this is a very common situation. It's very common that what you want to do is you want to run a low-pass filter where you are removing the high-frequency stuff, saying that that's just noise, and you are keeping the meaningful low-frequency stuff in the new smooth data set. In order to work with a Lanczos filter, you have to define a cutoff frequency. What is the frequency that you're going to define? Okay, if the oscillations that you're seeing in the data are shorter than this, remove them. So you have to define a frequency. Most of the time, actually, it's easier to think about it as a period. I want to remove things shorter than 3 months, or I want to remove things shorter than whatever, some number, and then convert that to a frequency using that frequency equals 1 over period equation that we used earlier. So just like the running means, Lanczos filters have a set of weights, and here happens to be the equation for a set of weights for a low-pass Lanczos filter. Here again we have weights Wj, where j is going to run from negative k to k, So you have a table of these weights, and you're given FC, which is going to be your cutoff frequency. That's what you have decided to use, where things higher frequency than that you want to remove, lower frequency than that you want to pass. Well, this equation is a little bit of a mess. It certainly is nowhere near as simple as the one that we used for the weights of a running mean, but of course those were just constants. As weights of a filter go, this is actually a relatively simple equation. So for each value of j from negative k to k, you can compute a value of wj, except in the case of j equals 0. You can see both in both of those terms there, we're going to have j, we're going to be dividing by j at some point, and so you're going to have divided by 0, so that doesn't work there. We will actually be able to solve for the weight at w0, where j is equal to 0, as sort of the residual. Remember, the weights should all add up to 1, so if we don't compute a weight at j equals 0, add them all up, we'll get a number a little bit less than 1, and then we'll just say 1 minus the sum of all the other ones has to be the weight at wj, where j equals 0. So it's a pretty straightforward procedure. Just you have to see it illustrated once or twice before you'll quite get the whole thing. Lanczos filter works really well, but it has a bit of bad news. The bad news about filters like these is that they tend to waste a lot of data. Whereas we were working with our running means with a value of k of maybe 3 or 12 or something like that, where we were working with a relatively small boxcar, the window size for a Lanczos filter or other bandpass and low-pass filters tends to be quite large. Typical value of k is something like 60. So remember, you can't compute filter data for the first k observations or the last k observations of a data set. Well, when k was 3 or 4, we weren't losing that much data. On the other hand, when the value of k is equal to 60, you're losing the first and last 60 values in your data set. Well, like in our case, we're working with monthly values of the Southern Oscillation Index. 60 months is 5 years. We're losing the first 5 years and the last 5 years of data. That can be a problem. And different filters use different values of these window sizes and so on, but in general this is a problem for filters. But as you'll see, for lots of purposes, the benefits that you get from using a filter over using something as simple as a running mean way outweigh the fact that you have to throw more data away. So let me do an example here of an implementation of a Lanczos low-pass filter in Excel. Let's take that SOI data that I've been using all along, and we're going to use a Lanczos filter on it. And it's going to have a cutoff period of 9 months. That means I'm going to try to remove oscillations in the original data that have a period of less than 9 months, and I'm going to keep everything that has a period of more than 9 months. At least ideally, that's what I'm doing. As we'll learn in the properties of filters lecture, we don't quite get that, but it's close. Okay, so 9 months, we have monthly data. That means we have 9 units here that's our cutoff there, which makes the cutoff frequency 1 over 9, or 0.11111. Okay, so that's going to be FC, our cutoff frequency. Now we have to compute the weights. There's going to be 121 weights, because k is equal to 60, and the number of weights is 2k plus 1. So we're going to have weights wj from j equals negative 60 to j equals positive 60. So to facilitate that, I'm just going to make myself a column here that has the numbers from negative 60 to 60, just to help me keep track of this here. And it's a big job to get that big equation in there right. It's going to take some fussing. That's a fairly messy equation for Excel. But you plug all those numbers, that big equation in there for those weights that was on the previous slide, and you'll get the first weight. Now the first weight at j equals negative 60 is a very small number. But when you copy that down across all from j equals negative 60 to j equals 60 weights, you're going to have some of the numbers are bigger and some are smaller. And you'll notice if you scroll down to the number that corresponds to the weight at j equals 0, you have an error there. We talked about the fact that you can't compute the weight at the point j equals 0, but here's a neat trick. If you go ahead and just set that weight for the time being to 0, and add up all the weights using the equals sum function, you're going to find out that you're going to get a number slightly less than 1. Well, the numbers should add to 1, so apparently the part that you're missing is the part that corresponds to the weight at j equals 0. So just take 1 minus that sum and copy that value to the clipboard. then go back to where you were getting that division by zero error at j equals 0, and you're going to need to paste that value in there. Now, if you just hit paste, though, you're going to have a problem with references and so on. You need to do the special paste. I don't know on a Mac how you do it, but on a PC, it's Alt Edit Special Values. It's Alt ESV on a PC. I'm sure that if you go into the Edit menu and then you see Paste Special, and then you'll see values, and that's what you paste in, because you just want to paste the number, not the equation. All right, so if you go back into your spreadsheet, you're ready to compute the low-pass filter, and this is done using a convolution again. Now you're going to be convolving the raw data with the 121 values that are your weights. So again, we're going to go down in our data, skip the first k values, because those the filtered value is undefined for the first k, though you have to lose those data points. But then starting at the kth plus 1th value, we're going to do a convolution or a sum product. So you equals sum product, open parentheses. Then drag your mouse across the first 2k plus 1 values of the data set, which is 121 values. You see there's some visual cues on the screen to tell you how many rows and columns you've selected. All right, so you've selected 121 values. You press comma. Then drag the mouse across the 2k plus 1 weights of the filter and press enter. And of course, it will have computed a filtered value at that point, but we can't copy that equation down just yet because remember, the references to the weights have to be absolute references. So you have to use F2 to go back into the formula here, and you're going to change so that the part of the function here that refers to the weights is an absolute reference with dollar signs in front of the rows and columns. Then copy that, paste that formula down to all but those last k observations, and you will get a low-pass filtered, Lanczos filtered data set with a cutoff frequency of 9 months. Now, I've plotted that on this particular diagram here, but when you look at the full 100-plus years of data, it's a little hard to see what has happened. So again, let's zoom in on just the last, or just a 10-year period of the data there. And again, the data with all the wiggles in this graph here is the raw, and the curve that's so nice and smooth there is our filter data. And you can see it did a very nice job. It represents the large-scale trends, but anything with a period shorter than about 9 months has been removed from the data. And this might be preferable for certain statistical tests or certain kind of purposes over working with the raw data. Now, of course, the trade-off here is we ended up losing data at the beginning and the end of our data set. We have raw data for the first, for the whole period, including the first 5 years and the last 5 years, but we can't, unfortunately, compute filtered versions of the data set during that time period. We have lost that. But it's a trade-off. We have a smoother, easier to work with data set that has certain nice properties, but we have lost some of the original data as well. Filters, as you're going to see in the Properties of Filters lecture, have much better properties than something as simple as a running mean. Their behavior is more predictable. They are going to be useful for certain purposes that a running mean is not, but they are going to waste a lot more data. You have to have a lot of data to work with at the beginning and the end of the time series because you're going to lose so much off the beginning and the end of the time series. This was all been a low-pass filter. Just to show you how it's done here, we also have bandpass Lanczos filters. Now, a bandpass Lanczos filter has two cutoffs. There is a long period cutoff, FC1, and a short period cutoff, FC2, because you're only going to be trying to keep the data, you're only trying to keep the oscillations that are happening on time scales between the FC1 and FC2. Anything outside of those ranges, you're trying to get rid of longer frequency and shorter frequency stuff. And so here is the function that you use to compute the weights from j equals negative k to positive k. And again, it's not actually all that much different than the equation you used for the low-pass filter. It's just slightly different. It is a bit of a mess, and if you look through it carefully, you'll see that at j equals 0, you can't compute it. You could either solve for W0 using the technique we used before, where we added all the other values up and then just took 1 minus that sum. Or in this particular case, L'Hopital's rule can be used to save us. That's a stunt that you learned back in Calc 1, I believe. But as it happens, L'Hopital's rule does apply here, and if you use L'Hopital's rule, you find out that at W0, the value is actually quite simple. It's just 2 times the difference between the two cutoff frequencies. Anyway, once you have these weights, you just convolve these weights against the data just like you did for the low-pass filter, and you'll have bandpass filter data, and we'll have some videos demonstrating how that's all done for you. But hopefully this kind of gave you a quick overview of how filters work and what you can do with them, and how to do them in Excel, and we'll see some examples and we'll learn about their properties in further videos. Okay, if you have any questions, let me know. This has been Dr. John Schrage.